In school, you learn about the life cycle of a star and where a star will eventually end up, namely a white dwarf, neutron star, or black hole. But you never really learn what these objects are beyond just dead stars. So let's learn about them a little more. But first, let's review the life cycle of a star. During the prime of its life, a star is held stable by a balance of gravity and the pressure created by the nuclear fusion in its core. Eventually, the star will run out of hydrogen and start fusing heavier elements, causing it to swell into a red giant. And when these other fuel sources fail, the star will lose its outer layers as either planetary nebula or supernova. The core is left behind, but without any fusions counter the force of gravity, it is squeezed into a small, incredibly dense object, either a white dwarf, neutron star, or black hole. A low-mass star like our Sun will end up as a white dwarf, a glowing ball of carbon and oxygen similar in size to the Earth. White dwarfs have a density of 10 to the fifth grams per cubic centimeter, roughly a ton per cubic inch, and this leads to something called electron degeneracy, which means that the electrons are pushed as close together as possible without breaking the laws of quantum physics. This creates pressure to keep the white dwarf stable, but also makes it where it has to be less than 1.4 solar masses, which is called the Chandrasekhar limit. A solitary white dwarf will over trillions of years use up its remaining energy and cool into a black dwarf. But a white dwarf in a binary system can pull enough hydrogen off of its companion to temporarily reignite fusion and send a burst of hot glowing gas into space, creating a nova. This process can repeat over time, and the white dwarf can eventually gain enough mass to exceed the Chandrasekhar limit, which results in a type 1a supernova. A star with a mass greater than 8 solar masses will become not a white dwarf but a neutron star. Neutron stars result from the collapsed iron cores of massive stars and are so dense that the protons and electrons inside of them have combined into neutrons and have diameters of about 20 kilometers or 12 miles. Pulsars, short for pulsating radio sources, are rapidly spinning neutron stars that emit powerful beams of radiation. Like ordinary stars and white dwarfs, neutron stars can be found in binary systems where they will eventually collide, fusing heavier elements than a star ever could and creating a black hole. A star more massive than about 20 solar masses will collapse to a black hole. These impossibly dense objects don't emit radiation and are practically invisible, but they do have gravity, charge, and angular momentum, and we can detect how these properties affect the objects around them. A star or other object in the gravity well of a black hole will either go into orbit around it, or if it gets too close, will be torn apart and fall in. But black holes don't simply collect matter until they fill the universe. Quantum processes can form pairs of short-lived particles that will normally collide and disappear. But if this happens near the event horizon of a black hole, one particle can fall in while the other one escapes, taking with it some of the black hole's energy and mass. This process is called Hawking radiation, and it means that black holes, like everything else in the universe, eventually decay. However, a one solar mass black hole would take 10 to the 67 years to evaporate, way longer than the current age of the universe.